How many do you have? Two. Alexis? Three. Sir again? Three. So that two. Two, okay. All of them take home or in class? Take home. Okay, so let's continue our talk. Last time we talked about it is a J integral, and we also talked about the CTOD, the relationship between the J and the CTOD. Also, we talk about it here. Okay, so we are here now. J control the fracture, and J can completely characterize crack tip conditions. In this case, the J is interchangeable to the CTOD. So that means we can call this J control the fracture implies a CTOD control the fracture. So that means that we have elasto plastic deformation. So however, fracture mechanics analysis based on the J and the CTOD become suspect when there is excessive plasticity or significant crack growth. So in such cases, fracture toughness and the J-CTOD relationship depend on the size and geometry of the structure of the specimen. So you need to know that, okay? So these are J controlled and the CTOD controlled, and they are only applicable for this relatively small elastoplastic deformation. Definitely for the linear elasticity, this is totally fine, okay, for these two. But if this is plasticity is huge, excessive plasticity area is huge, or the significant crack grows, very, very fast and in very, very big increment, and so CTOD and J controlled, and this is analysis, they are not valid. And so here I just draw the several figures. Okay, so for first one is a small scale yielding, and second one is elastic plastic conditions, and the third one is larger scale yielding. And for first one, you can see that for small scale yielding, and you know the small scale yielding, right? Whenever we talk about the small scale yielding, and you know what conditions must be met in order to guarantee that. So this guy is in the small scale yielding, right, guys? Do you still remember? What is the size of A? What is the size of W? And what is how they are related to using the yield strength. So for small scale yielding, and for small scale yielding in big area, okay, so big area is a dominated zone. For the K is a dominated zone. That means in this area, and we have elasticity. So this is a K dominated zone. And the J dominated zone, we can go a little bit further down. We have J dominated zone. And however, for this large screen zone here, and so this is no single parameter characterization. And for this is for larger screen zone. For example, look at this figure, okay? For this figure, so this is the log sigma yy. This is in the y direction, and so here's a logarithmic this is relationship, and so this R is this is crack tip. This is crack tip. So here is a relationship. This is R, the distance, and this is L is the size of the structure, and this is characteristic of size of the structure. R is the location you are interested in. So you can see here, okay, so in this area, okay, for big area, and because it is elastic, and you can still use LEFM to characterize this part. Okay? And for this, this is a smaller area, for J integral, for smaller area, and you can use the HRR, so this curve, so this is the straight line, okay, so this curve, using this curve, okay, so use this curve to approximate. However, if you have this is the plastic zone here. in this inside this plastic zone, and you can see, so this HRR is not valid. You understand, guys? What I want to tell you is that for this area, I can use LEFM to approximate. In this is a further closer area, I can use HRR. However, if the R is very, very close to the crack tip, in which there is a larger strain zone, and the HRR fails. HRR cannot predict accurately. You understand, guys? So RK, you can see, RS is the radius of K dominated zone. And this we can use the RK here also. For second elastic plastic condition, where J is still approximately valid, but there is no longer a K field. You can see here in this area, so this is LEFM. This LEFM differs substantially from this curve. Okay? That means for this condition and this condition, LEFM fails. LEFM cannot give us the valid answer, valid solution. But however, still in this J-controlled area, usually is a smaller area than the K-controlled area, and we can still use HRR to approximate. And once again, for larger strain zone, which is near the crack tip, and the HRR, the approximation also not valid. So this is what these two pictures says. The third one is larger scale yielding, and for larger scale yielding, no J controlled zone. J controlled zone disappeared. Okay, so that means no zone that could be singly characterized by using J integral. So that means you cannot use single parameter to characterize the crack tip field. And what you need to know, and you need to use multiple parameters. And this is what we are going to talk about today. You understand, guys? You can see, look at this picture. So you can see LEFM fails, HRR fails also. That means you need to use another approach to characterize the crack tip field. Questions regarding these three? Okay, my bottom line is that if I give you these three pictures, you need to use should be able to use your own language to interpret all of them. Right? You understand, guys? Okay. So then we look at about this HRR zone. Okay? So this sigma ij and the sigma ij, if we have the ki, you can see we have ki, we have sigma zero. Sigma zero is usually the reference, is called reference stress, and it usually equals the yield strength. Write down, guys. If we have not written down, I would suggest you write down. E is Young's modulus, nu is Poisson ratio, n is the hardening exponent, alpha is dimensionless factor, and this R is the distance of the point of interest to your crack tip, and theta is the orientation from this crack tip, from the point of interest to the crack tip, and A is, this is crack length, and this is L is the size of the characteristic size of the specimen. Usually is the length of the ligament. Question.
What is alpha again?
Alpha is a dimensionless factor. Alpha is a dimensionless factor. A is a crack length. L is a characteristic length. Usually is a ligament length. You understand, guys? So, for any fracture problem, so this equation we can denote this stress field sigma ij using this one, right? So Fij. But in addition to Ki and sigma and E nu n alpha, they are implicit material parameters and we just ignore them, and they are because they are implicit, and also because this crack length is usually much larger than the K controlled this is zone radius. R is the radius of K controlled zone, and A is far is much larger than the RK. Also, the characteristic length L, and which is usually the ligament length. So this guy's length is also always far higher than this RK. So these two guys and these two guys can be omitted also. And you can see, so we can just dimension make them. All this is characteristic. All these quantities dimension is sigma ij, and we divide the sigma ij using the reference sigma 0 and fij, and we still use this one actually, and we should use different note, different the letter, and it doesn't matter. Okay, so as long as you know that this fij is kind of different from this ij, at least in the format. So here's a ki, and because ki this guy and has the dimension of sigma multiplied by this r, right? So the theta. So you can see up to now, both this left hand side is dimensionless, and also these two parameters and their dimensionless also, and the theta is dimensionless itself because this guy is already the dimensionless one, right? Theta is just the angle, right, guys? Okay, so we know that. So this is because we have this ki is ki can be equal to E prime multiplied by J, and then you can just put this is the J here. So it's sigma ij divided by sigma 0, and we can express the ratio of these two guys using E prime. E prime is effective Young's modulus, and J integral value sigma 0 is reference stress. R is the distance between the point of interest to crack tip, and this is theta. And so this is for R is less than Rj. Rj is the radius of the J controlled area. Right? You understand, guys? Now, so HRR solution, and we have this HRR solution, so we talked about this one already. So this is sigma ij wave is a dimensionless function, and which is a function of n. N is a material hardening exponent, and theta is the orientation. And so this is HRR singularity is the special case of equation 3-60. Can you write down, guys? 3-60 is the equation 3-60. But the stress exhibits R, you can see R here, minus 1 over n plus 1. Because R is a part of denominator, and so this is the minus sign here. Dependency only over a limited range of R, so a limited range over. Or we can also say that HRR solution is a special case of J control. So we can say that HRR solution is a special case of J control. Any questions regarding from here and to here? So we want to write the dimensionless quantity in terms of J, right? In terms of J. We want to compare this one with HRR. So as I said, this one, right? HRR singularity is a special case of 3-60. This equation 3-60. So questions? So no question. I will talk about the growing cracks. So usually, if there is no plasticity, the crack will grow very quickly, right? Do you guys agree? So this we call the cleavage. cleavage, the cleavage. And cleavage means that there's no plasticity, and this is only the elasticity. If there's a crack grows, the crack will go from the very beginning to the very end. Very end means that this whole specimen goes, breaks. There's no elasticity. And however, if there is elasticity and the things are changing, how it change? The crack will not propagate immediately. And what is the first stage of crack propagation? It's blunting, right? So this is my sharp crack. You can see, can you do my hands? At the very beginning, so this crack is very sharp, and at the very beginning, it will apply load because of the plasticity. So this guy will be blunting. Okay, blunting means that the crack tip does not move, but this is two crack faces, and they are going away from each other. So this is called blunting. So this is blunting. This is called blunting, the J control. So this one, sigma ij divided by sigma 0 Fij1. This one means the first stage, is called blunting, and it is a function of J integral and theta. So second one, the stable growing, is no longer J controlled and stable growing. Now, after blunting, the crack tip here, you will have a small sharp crack here. Alright? So this is called a stable growing. So stable growing. Now, in addition to this term and this term, we also add a new term. New term is delta A. Delta A is a crack increment. Delta A is a crack increment. And delta I is a CTOD as an initiation of stable theorem. And we call this stable theorem. So this delta I. So this guy is a function of these three terms. So the third stage, steady state growth. You can see, I have this crack, this sharp crack, growing, and until now, maybe until the whole specimen breaks. You can see for this case, okay, and for this case, and we will have no control, but we will only have two terms. So this is the third term, in this equation disappeared. So when the crack grows well beyond the initial blunted tape, a steady state condition is reached, where the local stress and strain are independent of the extent of crack growth. That's the reason we don't have these terms. And please note, this function and this first function and third function, they are different, right? Even though they call it sigma ij, but there is a superscript. This is 1 for the first stage and 3 for the third stage. Are you guys okay? So my bottom line is that you should know how to use your own language to interpret, to tell me this figure. If I give you this figure, can you use your own language to tell me for each of these three stages what happens? For each of these three stages, and how we describe the sigma ij over sigma 0. Why? Okay, so you need to know that why we have blunting first. Can somebody tell me why we have blunting first here? Bobby?
Is it because of plasticity?
Yeah, plasticity. I want you guys to write down. Okay, write down now. Why we have blunting now? Because before the crack grows, and there is a plastic deformation in front of crack tape. So this plastic deformation can consume more energy, additional energy. That's the reason you need to go this way, okay? And then crack. Okay, so the key is why it is blunting? Because of the elastoplasticity. Without plasticity, what will happen? It will grow all the way down. Right? They grow this way. There's no blending. It's just grow like this. Questions so far? So no questions, and then we talk about this, okay? We have talked about this one, and for large scale yielding, for large strain, we know that HRR fails, LEFM fails. But here, what should we do? Right, so we will introduce another one. So for this one, because I just want you to know this, okay? So don't worry, guys. So crack tip constraint under large scale yielding. Large scale yielding is opposite to small scale yielding. On small scale yielding, we can use J integral to describe. But for large scale yielding, no. Okay? For large scale yielding, we need to use multiple parameters, multiple parameter model or models to describe. And we are going to talk this one now. So there are the genius, McClintock. This is a Professor McClintock, and he, I don't know, he or she, and the professor applied a sleeper line theory to estimate the stresses in a variety of configuration and plane strain on fully plastic condition. So here, okay, so you can see here. So this comparison of plastic deformation pattern in small scale yielding. So here is the first one with the slip patterns and the full plastic condition in 3 configurations. The estimated local stress are based on the sleeper line analysis of McClintock. So here, and apply only to non-hardening material. This non-hardening material. So this is from this is from this is a paper. This is from a paper. Yes. Master treatise. This is 1971. Okay, so this paper is even older than me. Right, so this is a small scale yielding the dented panel. The panel means a specimen. So this edge cracking in bending, if you bend, you can see this is a plasticity. So this shaded area is a plasticity. So this center cracks the panel. If you apply this load, you will see this kind of the plastic deformation. So large scale yielding depends on specimen shape. You can see different specimens. They have different. This is the pattern of the plasticity, the areas. So it is dependent on the specimen shape, and stress are not unique, but dependent on geometry. Yeah? Same address, the same stress, but you will have different. Same loading, but different stress distribution. So for bending type specimen, crack, this edge crack, we bend it this way. So here is a bending, and so here is bending, the bending moment. Also here is very similar, and then this is a 3-point bending. So this point is fixed, and we have force applied here and force applied here. And for this is a bending specimen moment, the constraints are relatively high, right? So here they use 2-parameter characterization, and they use this one to describe sigma ij. You can see, so this is what we have now, what we have learned, and ki divided by 2 pi r fij theta. R is the distance between the crack tip and the point of interest, and theta is the orientation of this point of interest and to the crack tip. And now, in addition to this ki, and we also need to have, so this is the tensor. And so this tensor is a 3x3, and we have T here, right? Okay, so this one is called an KT model. Write down this. So this model elastic T stress, and we this way called a KT model. It means that you need to have K and also you need to have T and to characterize the field, the collective field. So if we can see back, for small scale union, this is for large scale union. But for small scale union, we can treat this small scale union as a special case. For the large scale union, that means for small scale union, we can just treat this T equals 0. And then, so this equation reduces to this one, which is our the old friend, right? You understand, guys? So T is a uniform stress in the x direction, and which induces a stress nu T in the z direction in plate string. Nu is the Poisson's ratio. Nu here is a Poisson's ratio, guys. Questions, guys? So because the sigma ij is a 3x3 tensor, right? You guys still remember? Sigma ij is a 3x3 tensor, right? So I can just look at the sigma xx in the x direction, and so we have ki 2 pi r fxx this in x direction theta, and then plus t plus this value. This is sigma xx. So however, when theta equals pi, what does that mean? Theta equals pi. This is x and this is y. So here is theta equals pi. Theta equals pi. For this one, and theta equals negative pi. Right? That means theta equals pi is the top crack face. Top crack face. So for top crack face, fx x equals 0, and there is no traction. Okay, when there is no traction, and we assume on this crack, within this crack, there is no traction. The crack free, the traction free. Right? The traction free, or you have traction. When we will have traction, if we have some air. If we have pressure, we put some pressurized air here, and then we will have the T. The T will not be equal to 0. But for this one, for this crack, is no traction, and no traction. No traction means that T1 equals T2, both of them are equal to 0. And as a result, for theta, when theta equals pi, fxx, this equals 0. As a result, sigma xx equals the T. Right? So from here to here, we just want to rewrite it. So the first term is the same, but second term, except instead of using this as a matrix, I just use this is the delta function. Do you guys know delta function, guys? You know delta function, right? Delta function is delta ij, right? Delta ij equals 1 if I equals j. I equals 0 if I is not equals j. Right? This delta function. So this term and this term, they are the same. Okay, then we talk about bioactivity ratio. Bioactivity ratio is defined as the beta divided by tau t, okay? I can see t is sigma xx. T pi a divided by ki. So if beta is greater than 0, that means it's a high constraint specimen. If beta is less than 0, it's low constraint specimen. So we have 3 case scenarios. So this is bending, positive T, we have positive T. And this is also bending positive T. So here is a central crack. This is a tensile loading, and we have this here is a minus T here. For laboratory specimen with Ki solution of the form in table 2.4, so the T is provided using this equation. Okay, so this is how we calculate the T, and we use this equation to calculate, and using table 2.4. Table 2.4 and tells us for each of these specimens, we have multiple specimens, right? For different specimens based on geometry and how to calculate the K. The P here is the loading, the load, right? So I would suggest you look at the table 2.4 and to take a look. You can see, and these are 4 commonly used specimens: SEB, SENT, DENT, and CCT. Questions, Sora? Okay, so this is called KT theory, guys. Can you write down? It's called KT theory, right? And for this model, we need to have Ki, and we need to have T in order to describe the crack tip field. And then we look at our next model. The next model is called JQ theory. The JQ theory. So JQ theory, what's the JQ theory? And this is also, you didn't know that this is our second 2-parameter model. Our first 2-parameter model is a KT theory. So this is our second 2-parameter model that are used to describe the large scale union. Right? So assuming the small string theory, the crack tip field deep inside the plastic zone can be represented by a power series, the small string, where the HRR solution is a leading term, and the higher order terms can be grouped together into a difference the field. That means, so this one, we still assume it is a small string theory. So sigma ij can be written as, this is the HRR model, sigma ij HRR plus sigma ij difference. So the difference actually is the sum of all other terms. Okay, so sigma ij can be written in terms of this sigma ij HRR and sigma ij differ. Now, alternatively, the difference field, this guy, can be defined as a deviation from the t = 0 reference solution. So this can be defined as a deviation from the t = 0 reference solution. So that is different from the KT model. So that means sigma ij equals, excuse me, sigma ij when t = 0 and plus sigma ij and differ. So these are the two genii, Dao and Shin. Observe that the difference field, this field, is relatively constrained with both distance and angular position. Distance and angular position in the forward sector of crack tip region. That means for this region, okay? For this shaded region, theta is less, the absolute value of theta is less than half pi. Guys, can you imagine? This is my craft tape. I draw a vertical line. This shaded area can be represented using this inequality, right? Theta is less than half pi. This absolute value. So they found that the sigma YY diff is approximately equal to sigma XX diff, and these two guys are greater than sigma XY diff. And as a result, they just like sigma ij is defined whenever there is an equation sign plus delta means it is defined. Okay, it's defined as sigma ij t equals 0 and when t equals 0, and then q, which is dimensionless one, sigma 0 is a reference, and sigma 0 is reference stress, and which usually equals sigma ys. And then I have delta ij. And delta ij, what delta ij? This is the delta ij. If I equals j 1, if I is not equal to j 0, what does that mean? It means that so this equation is only valid for normal stress. What? When I equals j, because you can see sigma yy and sigma xx, they are approximately the same, but both of them are very, very much larger than the sigma xy. Sigma xy is a shear stress, right? Okay, so that's the reason I can use this one. Sigma ij, when I equals j, that is normal stress. When I is not equal to j, is shear stress. Right, guys? Okay, Q. The Q is defined as sigma yy minus sigma yy when t equals 0 divided by sigma 0. And for also, and when theta equals 0. So our sigma 0 j equals 2, j divided by sigma 0 equals this is delta t. Delta t equals this delta t here. Right? So this is you can see. So classical single parameter fracture mechanics assume that fracture toughness is a material, the constant. With the JQ theory, however, an additional degree of freedom has been introduced, and that means Q, which implies that the critical J value for given material depends on Q. That is, J critical is the function of Q. That means, so J is critical is you cannot use a single parameter model to describe the field. You need to have both J and Q. So okay, as Q goes down and the constraint goes down, J critical goes up. So this one JQ toughness locus for this. You can see this Q value is GC value. You can see not just the GC but also Q. Alright? That means one single parameter model fails if the process is large deformation for large scale unit. Questions so far? We have learned the KT theory, we have learned the JQ theory. And why I ask you guys, and I'm going to ask you guys quantitatively, okay? And how many two parameter models we have learned to describe large scale unit? Two. One is KT theory, one is the JQ theory. So then we take a look at next section. The failure of effect of failure mechanism on the JQ locus. Different failure mechanisms and have different effect on the GQ locus. Okay, the GQ approach is descriptive, but not predictive. It's descriptive, but not predictive. That is, Q quantifies the crack tip constraint, but it gives no indication as to the effect of constraint on the fracture toughness. A GQ failure locus can be inferred from a series of experiments on a range of geometry. Alternatively, a micromechanical failure criteria can be invoked. So there are two models here. Our first one is the Ricci not Rice K. This is RKR model method for cleavage fracture, which states that a fracture occurs when a critical fracture stress sigma F is exceeded over a characteristic distance RC. So what this RKR says, it says that, so here is my crack tip. In front of this crack tip, which is RC, okay? At that point, if the sigma F is when the critical fracture stress sigma F is exceeded at this point, if the sigma stress value exceeds this is sigma F, and we say the crack will go, and also the crack length, the crack increment will be this RC. So we use this GQ theory, right? Sigma ij HRR Q sigma 0 delta ij, and fracture the criteria, okay? As this is what this statement says. And we want to know that when R equals RC, the Y stress sigma YY equals sigma F, right? So this is what the model talks about. You guys agree? So we want to solve for this equation, and we want to see under what condition, because sigma F is usually the parameter, and sigma YY, and we can see so here, okay, so here this is HRR sigma F sigma 0, and we have this one, and sigma YY wave, and this is theta, because that is in this is a horizontal direction, and theta equals 0, and so this is plus Q. So sigma F divided by sigma 0, we have this one, and also if Q equals 0, we will have this one equals 0. So on J0, we call high constraint the toughness. Now, we just put this guy here, okay? So this sigma F minus sigma 0 minus Q divided by sigma F minus sigma 0. So this is JC, okay? Is a JC, and so this is J0, J0, 1 over n plus 1. So this gives us, okay, so this gives us JC, Jn0 can be written as 1 minus Q and sigma 0, sigma F, and exponent equals n plus 1. So J0 is obtained from experiments. So sigma F is material parameter. Any questions so far? So using this equation, and we can get TC. And use, as I said, and TC is a function of Q. What? You understand this? So J0, and J0, you can obtain the J0 using experiments. And you can use this equation to write TC in terms of Q. So this is the RKR model. Then we look at another model. Okay, so this one describes the relationship between TC and Q, and the shape of GQ locus depends on the failure mechanism. And the fracture is the stress control. Fracture is a stress control, and GC is very sensitive to Q, such as cleavage in metals. So, however, this is a stress control. Okay, you apply stress. However, strain control, and because for this one we compare the stress at a certain distance RC and with the sigma F. This is a stress control. And then we look at the strain control. And the strain control fracture is less sensitive and to the crack tip constraints. And suppose that fracture occurs when a damage parameter phi, which is a critical value RC ahead of crack tip, and phi is given as, and we use this equation. So I'm going to stop it here now. So Monday, and we are going to finish this part. We will have class Monday and Wednesday, right?
Yes.
The fall break starts from the Thursday.
Yes.
Okay.
And ANSYS is due Wednesday night.
Can you give me before Wednesday, before you leave for break? Okay. Okay, guys, last time they didn't ask me a question about the geometry of the specimen, okay? And I found this discrepancy when I talked to you last time, not the last time when the data asked me, another time. As long as your geometry is consistent, I'm fine. Okay? Be consistent, that'll be okay. Okay, guys, so I will hope you have a wonderful Friday, the Friday again.
Yes, thank you, Dr. Ma.
You're welcome. Okay. Yeah. What's the value rate? A0 is the initial crack length. Yeah. Yeah.
Yeah.
But this A is yeah, R, I mean R is a function of A.
Yeah.
Yeah, you need, huh?
Yeah.
You need to, yeah, this is a function. If A changes, and R will be changed, right? Yeah. A0 is known. A is a independent variable. The R is a dependent variable. If your A changes, the R will be changed. Yeah, this is a function.
Yeah, gotcha.
Yeah, the A can
I
be
don't
multiple
think so.
values, then the R will have multiple values also.
Oh, okay. Should I assume the A value?
You do not assume a value.
Fine.
Yeah, the curve, any curve.
Oh, okay, yeah, gotcha.
Yeah, the curve. Go. How can I help you?
I also have some questions about the midterm. So, mine are just on the short answer. When you ask for like types of loading that, the crack experience. I
Yeah.
looked through the notes and couldn't find anything, but,
The type of loading, right?
yeah, I just said shear stress, tensile stress, and then shear stress on like parallel.
No, what I'm talking about is the three crack mode. Opening, sliding, and curve.
Okay.
Yeah.
So,
Yeah,
I mean,
this is-
with shear tensile and then tearing. It's
Yeah.
kind of what I said, so it's
Yes.
like
that's correct, yeah.
that,
In the
that's,
type, yeah, at least the type of loading, yeah.
okay, that's fine then.
Yeah, the three basic
Okay.
modes, opening, sliding, and curve.
I'll write that too.
Are you okay, Dylan?
Yeah, I had a question on the derivation before.
Yeah.
Is that all you have to do for that? 'Cause
Supposedly no.
It didn't feel like enough.
Yeah, look at my lecture notes, okay?
I did. And like, these are the two equations it gives us.
Yeah, I'm,
So,
look at the lecture notes. Look at the lecture notes.
well, I did,
Yeah, my lecture notes says this.
yeah, it gives this and then just goes like straight here. But
Yeah, that's
I
good.
don't. Like. I don't, there's no part,
No derivation, no other derivation.
like I couldn't find at least part like deriving this.
Yeah, I think I have a little bit longer derivation. If you cannot find, I'm okay with you give that. But I want to look at bigger, deep, yeah?
Yeah.
Good.
For the last question on the midterm, where it's asking, like, show relationships between K, G, and J, is there like a place in the notes that we can find that?
Yes,
The one place I found it was in the lecture you were talking about today, where it was talking about,
not today, I just mentioned refresh memory, what we have learned.
yeah, because it talks about low level deformation